Hi, this is Devargret. I am studying in Institute of Aeronautical Engineering. I am studying BTech first year Computer Science Engineering. Today we are going to discuss about corrosion of electronic resistor. Resistor is a device which opposes the flow of current through it or flow of electricity to it. Damaging of electronic resistor. The electronic resistor can be damaged by inappropriate packing of resistor or incorrect functioning of the resistor and due to some catastrophic reasons. Mostly greater than the 20% of microelectronic devices are being failed due to the corrosion. Today we are going to discuss about corrosion of electronic resistors. These are the subtopics. Introduction 3 to 5 pages, precision with chip resistor 6th page, atmospheric corrosion 7th page, diffusion model 8 to 9 pages, experimental method 10 to 11 pages, results and discussion 12th page, and finally conclusion 13th page. We are going to conduct an experiment. We are going to take two types of resistors. Two types of resistors. We are going to take type. We are going to take two types of resistors and to 20 resistors, 10 each samples. Okay. In order for electronic components to function, so specification, reliability of device, packaging is crucial. Failures of electronic components and packages not only cause the malfunction of the devices themselves, but also sometimes lead to catastrophic failure of whole systems. Of all microelectronic device failures, corrosion-related mechanisms are estimated to be responsible for more than 20% of them. Surface-mounted chip resistors are often considered to be the simplest and most expensive amongst all of the components used in electronic circuits. The resistors are most cheap in electric circuits that we use. However, resistor failures in some systems are responsible for complete functional breakdown. Typically, resistor failure modes include open circuits, resistive shorts, or variations in resistance indicating intermittent failure. The physical condition and electrical characteristics of resistors may provide significant information about root cause of failure. This study focuses corrosion-related failure of precision thick chip resistors. Figure 1 shows view of main elements of chip resistor, typically the basic elements of a resistor are ceramic substrate, wraparound terminations, a resistor element between the terminations, typically made of silver, a glass overcoat over the resistor element, and a polymer coating over. This is the inner layer of the resistor. Inner layers. There are three layers in resistors: inner layer, protective layer, and outside layer. Outside layer. Inner layer. The elements in the inner layer are resistor element, ceramic substance, and silver coating. Resistor element is covered by ceramic substrate and it is covered by silver coating and it is covered by glass overcoat. Protective layer. Is covered Protective layer covers inner layer nickel-like elements act as protective barrier and outer layer is outer solar termination. Polymer layer is over the glass overcoat. As illustrated in figure 1, the wraparound terminations generally comprise three layers: a conductor layer on the inside and a solder layer on the outside, and a protective barrier, typically nickel-like elements, form the protective layer between the conductor and solder layer. The wraparound acts as a low-resistance interconnect between traces on a printed circuit board (PCB) and the resistor element. In addition, a thin conformal organic epoxy layer is typically applied to the resistor in order to impede the corrosion of the resistor by limiting the diffusion time taken for the water vapor and pollutant gases to reach the resistor surface. Due to high demand of surface mount thick chip resistor components, numerous different resistors are commercially available with a variety of designs. The scope of this work is to examine the failure mechanism of two precision thick chip resistors with distinctly different designs, which are representative of current resistor designs in printed circuit board (PCB) assembly and subject the resistors to a well-defined corrosive condition over 60-day period. We will take two types of resistors, type A and type B. One we will keep in the atmospheric conditions and one will keep normally outside. One we will keep in the vacuum. Okay, we will We will do experiment in the 5 layers. First layer we will check out in 5 days, next 10 days, third layer in 15 days, fourth layer in 30 days, and final layer in 60 days. We will replace the resistor. There are recent chip resistors that are used in variety of different industries, from telecommunications to automotive electronics, and such can be exposed to mild and aggressive corrosion environments. This paper investigates the corrosion performance of two generic precision chip resistors in a controlled corrosive atmospheric conditions of 60 degrees Celsius temperature, 4 ppm pressure, resistors and water vapor in purified air. The resistors were exposed in an environment chamber for periods of 5, 10, 15, 30, and 60 days in 5 layers. Following exposure, Following exposure, the samples were cross-sectioned and subject to the surface analysis using microscopy and microanalysis. After the initial stages of exposure, corrosion was observed only on one type of resistor. This we will conclude in the final conclusion. The corrosion developed because H2S gas and water vapor diffuses through the thin protective organic layer in the resistor and subsequently reacts with the silver conducting layer. Corrosion was facilitated by a poor overlapping of the solder and nickel layer, and in particular the glass blended over the glass overcoat before the polymer overcoat, which allowed silver and sulfur to diffuse along the interface. In addition, this poor overlapping allowed contact between the nickel layer and the silver layer, resulting in the development of electrochemical corrosion. The main corrosion products that develop silver sulfur and nickel sulfide residue. Atmospheric corrosion. Okay, in the graph you can see that there is x direction. At x equal to 0, the uh, the resistor is contact with the metal surface. At x equal to L, it is contact the well state fluid. Okay, corrosion can lead to the failure in a resistor. Atmospheric corrosion can lead to failure in a resistor device by reacting or removing the conductive material of the resistive element or device terminations, thereby leading to an increase in resistance. The literature reports that in that mainly silver reacts with sulfur to form a non-conductive silver sulfide layer, thick film, which can lead to open circuit some or all of the resistive elements in a resistor. Hydrogen sulfide and high levels of relative humidity have been identified as the primary atmospheric constitution responsible for the degradation of silver and some alloys, commonly used in electronic industry. As such, in this study, the combination of 90% of relative humidity and 4 parts per million pressure H2S is used as pressure works to represent a highly accelerated condition for the corrosion of the resistors. The high concentration of H2S is more suitable to give data for electronic components deployed in the Central and Latin America, Asia, and special Pacific regions. In order to accelerate the diffusion of gas and water vapor, the samples were exposed for a 60-day period at 90% relative humidity, 60 degrees Celsius, and 4 ppm H2S in 5 layers, 5, 10, 15, 30, and 60 days. Samples of each type of resistors were extracted from the gas chamber at predefined intervals, and a range of materials characterization techniques were applied to investigate the progression to failure of the resistor components. Diffusion model. The corrosion of the resistor is limited by the diffusion time taken for the water vapor and resistors. Actually, corrosion only caused by the diffusion of gas. Resistors gas. To penetrate thin conformal organic layer, a closed form analytical expression for the transition diffusion of species such as water vapor and H2S through a planar layer is presented here. The expression is used to determine time-varying concentration of H2 and H2S at interface between a polymeric coating and metallic substrate. Figure 2 shows the dimensions and boundary conditions of transition 1D diffusion through a planar layer. The following assumptions can apply. The thickness of the layer is negligible in comparison with any planar dimension. This imposes 1D mass diffusion in the x direction. At the plane of interest x equal to 0, the layer is in contact with the metallic layer, so mass transfer is negligible. Okay, mass transfer is negligible because it is in contact with the metallic layer. The surface of layer at x equal to L is exposed to a well-stirred fluid, so the boundary layer contributes negligible resistance to the mass transfer. There is initially a uniform concentration rho with a layer at time t equal to 0, and the layer is then exposed to ambient concentration rho at time t equal to 0. No chemical interaction occurs between H2O and H2S species, or between the species and the polymer layer. Between H2O and H2S species, no interaction occurs. Between these two species and polymer layer also no interaction occurs. The temperature of the layer is uniform. d square c by dx square equal to 1 by d into dc by dt, where c is mass of concentration in constant units. The units are given in the SI quantity, kg per meter cube or parts per million. D equal to coefficient of diffusion, 80 meters square per second. Experimental method. There are three ways in experimental method: sample preparation, generation of corrosion atmosphere, and analytical techniques. Sample preparation. Two different types of commercially available 100 ohm 1608 precision thick resistors were used for this study. Type A and Type B. Two types of resistors. Prior to corrosion testing, the specimen were rinsed with isopropyl alcohol and followed by distilled water and dried with nitrogen. So we need to take 20 resistors, 10 sample A, 10 sample B. Two types of resistors. To do the experiment, okay, to for corrosion testing, they need to rinse with isopropyl alcohol and then followed by distilled water, and next they should be dried with the nitrogen gas. Generation of corrosive atmosphere. The tests were performed over a 60-day period in 5 layers with the removal of 10 samples of each type of resistors. Type B and Type B, 10 resistors, totally 20 resistors we need to take. After 5 layers, layer 1 5 days, layer 2 10 days, layer 3 15 days, layer 4 30 days, and layer 5 60 days. After these 5 layers of exposure, the chamber had a volume exchange of 4 times per hour. A volumetric flow rate of 61 per hour, yielding a mean local velocity within the chamber of order 0.6 mm per second. Although this velocity is slow, it is evident from an assessment of connective mass. Transfer rate that transport within the gas phase is fast relative to the consumption rate at the surface. In order to achieve 90% relative humidity, a small liquid flow of water was fed to a mixing chamber in which the gas flow was directly controlled and mixed with the injected carrier gas. It is directly provided by gas, saying that H2SO4 ppm mixed with the purified air. H2SO4 and mixed with the purified air can be provided directly. Subsequently, this gas vapor liquid three states mixture was lead to the temperature control heat exchange. To achieve complete evaporation mixing, the H2S data was measured periodically with grab sample measurements made with German 631X meter Arizona instruments temperature agent. The gas and liquid flows were measured by Longest high-tech EL flow liquid flow controllers, respectively. The water was mixed with the gas, which was subsequently evaporated and supplied to an exposure chamber held at desired temperature. Pure copper coupons are also placed strategically in the chamber and used to conform exposure conditions. Analytical techniques. Samples were examined visually using a Leica Zoom 2000 stereo zoom microscope and then mounted and mechanically polished at a 1 micrometer diamond paste finish. After metal after metallographic preparation, After metallographic preparation, the microstructure were examined under a JTISS axioscope optical microscope (OM), a Geol JSM 840 scanning electron microscope (SEM), equipped with a Princeton Gamma Tech PGT energy analysis dispersive X-rays (EDS) system was employed to obtain a high magnification electron images and to conduct chemical analysis respectively. The resistor surfaces were studied using secondary electron mode. This mode does not offer atomic contrast, but enables imaging at higher resolution and is more sensitive to morphology of the specimen surfaces. Results and discussion. The image depicted in figure 4a shows stereo microscope image of resistor type A obtained in the as received conditions with figure 4b and figure 4c, showing cross section of left and right side of the coating termination boundary surface. Respectively, 4b and 4c shows both sides exhibited similar structure, comprising an outer bright layer of tin plumbum solder, approximately 10 mm thick. It's a thin plumbum layer is the soldering layer, the final layer of resistor above a darker nickel layer, approximately 14 mm thick. Nickel layer is protective layer with both layers overlapping the overcoat between 50 to 80 meters. The, the third layer and the nickel layer surrounds the edgy layer, surrounds the silver layer, which by overlapping the overcoats as sealed with the existing glass overcoat. Figure 4a stereo micrograph. It shows stereo micrograph image of as received type A resistor. 4b shows the left side of resistor type A and 4c shows right side cross section. Backscattered electron images of resistor. Coating termination boundary at interface LL and RL. Okay, in figure we will show first we can see overcoat, it's overlapping, next edge layer, next SN and PB layer. Both layers are overcoating. Nickel layer. Third layer is a SNPB layer and nickel layer overcoating. First inside layer is aluminum substrate. Conclusion. Corrosion of type B resistors occur after 5 days exposure and continue to develop up to 60 days in 5 layers to 90% relative humidity, 60 degrees Celsius and 60 degrees Celsius temperature and 4 parts per million stress pressure, while type A resistors showed no signs of corrosion. It can be detected that corrosion of type B resistor was due to reactions between the sulfur environment and the silver layer, creating an electrochemical corrosion cell between Ag and nickel layer. The main corrosion products that develop are Ag2s and nickel sulfur residue NHS. The root cause of corrosion can be attributed to poor overlapping of the solder and nickel layer. Third and second. It means outer layer and protective layer overlaps so that corrosion takes place. And in particular, glass blinder over the glass overcoat, which allowed silver and sulfur to diffuse along the interface. Furthermore, poor overlapping permitted contact between the nickel layer and edge layer. Okay, nickel layer and silver layer resulting in electrochemical corrosion. Thank you for